S-Chan presents educational video lectures. Difficult concepts made easy. Study anywhere, anytime.
Hello students, as we have done the different kind of differential equation and then the solution of the differential equation. So today we will learn about the heat and the diffusion equation.
If you want to study this topic in detail, refer to the book by S-Chan Publishing. Link is provided in the description box.
Welcome to the S-Chan Academy. My name is Kanhaiya Jha, and today we will focus more on the one-dimensional diffusion equation. Diffusion equation is basically a partial differential equation. Partial differential equation where we have again two variables, as we can see, du by dt with r and t, and then we calculate the variation with the particular two variables here. So this partial differential equation, which describe the density of a material which is undergoing a diffusion. So we will calculate density. The equation can be written by du by dt rt, where we have this particular value. So we have a variables r and t is the density of the diffusing material for location r, x, y, z. So diffusion we are calculating on the three particular axes, x, y or z axis. So wherever the diffusion is occurring, we can calculate it. We are using different variables to calculate this diffusion. As we can see that we are using r and t. So this du rt is denoting the coefficient of diffusion of the density at a location r, and then this particular coefficient of diffusion we are calculating it. So first of all, what we are doing is the diffusion rate we are calculating by using the different variables for a diffusion, and after that we are calculating this on a given position. The position can be any position on the x, y and z axis. The particular location or the particular point can be evaluated at any point from the particular x, y, z. Then we have a diffusion coefficient here. If you can see, this diffusion coefficient is du rt by dt, where we can calculate a diffusion coefficient. Then the total equation here, which is du by dt r dt, is called as the heat equation, and heat equation is generally description that describes the heat distribution over a given time or over a given particular position or a particular point. So with this diffusion, what we calculate is that we take the density with the different variables, and when we form the differential equation, that particular differential equation gives the heat diffusion at a different particular time. So we have the equation du by dt. This equation basically calculate the continuity equation, that whenever there is a diffusion changes going on or the heat dissipation changes going on, we can calculate it this by this particular formula, and here we can calculate the flux of the diffusing material. Flux in the sense that the total heat rays passing through. As we know that the flux is a totality of the field. So flux we can calculate by evaluating the total heat rays passing through a different point or a particular time or in a given range. So first, recalling this, we take the density. Density is expressed in two particular variables, r and t. Then we calculate a diffusion coefficient. Then we calculate the heat dissipation, that how the heat dissipation is calculated at any particular point. Either it can be calculated on the x, y or z particular point. At any particular point, the heat dissipation can be calculated, and from the heat dissipation we can calculate the flux change in the particular body. So the diffusion in the one dimension can be calculated as that diffusion equation in one dimension is du by dt xt, which is du square xt by dx square. So this is basically heat diffusion particular diffusion equation we are using in one dimension, and then we are taking a particular interval. So here we are taking the particular interval which is O and I with the initial condition, the ux0 is equal to fx. So we are taking this with a particular position, and the boundary effect that we are taking is 0 and t. So 0 LT is 0 is equal to 0 in the boundary condition. So we are taking this, we are calculating this one particular dimension where du xt by dt can be calculated here. Then we are taking the initial condition with a particular calculation, and then we are calculating it with a particular boundary effect. So we are calculating the heat dissipation, that how heat dissipated from the given particular density by this particular equation. But in this particular equation, we are making it for one dimensional. Either we can calculate it for the x axis, or we can calculate for the y axis or for the z axis. For any one particular axis, we can make the calculation. Then we have an analytical solution of this. We can use this particular solution, say that u xt is equal to xx xt. So we can make it a 1 by d, calculate t dash, and then calculating the x double dash. So this has a particular value where we can see that the value is coming in lambda. So this is for the conventional reason that conversion is taking place. The conversion is taking place is that a one form of the energy is generally dissipated into the other form of energy. So what we are noticing here is that one form of energy is dissipated into the other form of energy. So here we are studying this particular heat dissipation. Then here we can see that we can calculate it. It is a linear ordinary differential equation. We can calculate it xt, which is by this equation we are calculating the heat dissipation. So first we take two variables, then we calculate the one dimensional, then we calculate the flux density, then we calculate a change in the density, and after that we are making an analytical solution that how it can be done. Then we have to use this particular relation. These are the sequence what we can use. What we have to understand is uxt is summation of n is equal to 1 to infinity 2 by L integral of 0 to L. This is the particular equation. So again we start from the lambda is equal to 0 when the boundary condition is taken as to be 0, then lambda is greater than 0, and then the lambda is particular values, and then we are making this particular calculation. So the boundary effect is taken in such a way that we are taking it 0, we are taking it greater than 0, and on both the cases we are making the calculation of the particular differential equation, just to understand that how the changes can be analyzed, how the density change can make the heat dissipation change, and how this heat dissipation change can be calculated from the particular flux change. So we have this particular the heat diffusion equation that we have taken it from the previous value. So heat diffusion equation is basically calculated by this. This is called as a implicit method. Implicit method where we denote the value of alpha. Alpha is equal to d delta t by delta x square. So we can use this 1 minus 2 alpha, and then we can make the calculation. The final equation will be in terms of the heat dissipation. Again we can see that this relation which is I omega is equal to dk square. So we put the value in terms of the exponential and calculate it here, which is 1 minus 4 alpha sine square k delta x by 2. So we can write down here as I omega delta r, that is log 1 minus 4 alpha sine square k delta x by 2. So here this particular method can calculate for the 0th value also, for the less than 0 also, and for the greater than 0 also. Here we can use the I omega delta r for the 4 alpha sine square k delta x by 2, which is equal to k square delta t sine square k delta x by 2. This equation is basically what we generally use for the heat dissipation. When the density is changing, then we are calculating the change in the particular temperature, and the temperature will lead to the change in the flux. So first we started by taking the particular two variables. After taking the two variables, we calculate the change in the two variables in the one dimension. Then we fix up the range and the boundary effect. After fixing up the range and the boundary effect, then we put the values and calculate the differential equation. That differential equation enables us to calculate the different particular values related to the temperature, density and the particular flux. So here we can see the particular equation which is used at any point, which is used for the particular any particular value. Now we'll take a small break and then again we continue.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back, students. So we have learned about the heat diffusion equation. So we'll proceed further. So we have the one method which is called a Richardson method, where we improve the approximation order. So this method is used to enhance the approximation, and it is used to calculate the difference between the two particular time intervals. That if two time intervals are given to us, then how we are calculating the difference between the two particular time intervals and how to improve the particular approximation. So here we can see in this equation that we can see I plus 1, then it is I minus 1. This is the difference between the two time period. Then alpha we calculate, which is d delta t by delta x square, and then we will calculate this particular equation, g square plus 2 beta g minus 1 is equal to 0, where the value of the beta is equal to 4 alpha sine square k delta x by 2. So we make this particular equation that gives us that minus beta plus minus under root of beta square plus 1. So this equation, the Richards equation, is basically what we have seen here, that to minimize the particular approximation and then to calculate the difference between the two times periods. So where they can see that I plus 1 minus I minus 1 is basically the difference in the particular two time periods, that we are using this in the difference in the particular two time periods, and then we are calculating it. So here we can see the final value that we are getting is minus beta plus minus under root beta square plus 1. Then we have the Frankel method. The Frankel method is basically that shows the stability by using the particular algorithm, and you can see this particular equation, and this will be more clear in the next page. So here we can see that u plus 1 I plus 1 minus u I minus 1 2 delta, this is the equation that we can calculate. So basically this can be expanded by using the Taylor's method also. By using the Taylor series, we can make the expansion in this, and here we can see that the how we have come to the particular equation, and then what we can see that delta t over delta x is coming to be 0, either delta t is 0 or delta x to be 0. So we will get this particular value. So this is basically that how we lower down the approximation. Then we have BTCS implicit method. In the BTCS implicit method, we have a alpha, which is d delta t by delta x square. We are calculating the alpha with a change, and we are calculating the gk here is the amplification factor. So using the amplification factor, which is gk, which is 1 minus 4 sine square k delta x square by 2 is to the power minus 1. So basically this is the unconditionally stable, okay, and this method is delta t delta x square is basically that to calculate the, as we have mentioned in the slide, first order in time, second order in space. So first we will calculate the time, and then we calculate the particular position. So the time can also be calculated and the position can also be calculated. both the variations can be calculated very easily, that either we are calculating in terms of time or we are calculating in terms of particular position here. So this is the method. The next one is the Nicholson method, the Crank-Nicholson method. So it is based on the central approximation. That central approximation is basically the bisected value. So when we have two values and we bisect the value and we get the mid value, then central method we can see xt 1 by t delta t. So here we are using u I plus 1 minus ui 2 delta t by 2. So we are using here the central value, and by using the central value we are making the calculation to minimize the approximation. So again we have ui n plus 1 minus ui n by delta t, we are using this equation, and then in the final term what we will get is this particular equation, which is minus alpha u. So basically this method is used the central value, middle value also, that we have to calculate that particular value. When we have two particular values of the particular position or a particular time. So in previous method what we have discussed, that we were calculating the difference in the time or the difference in the position, and then we are making the calculation. But here in this particular case we are not calculating the difference, but we are calculating a particular center value or a particular middle value, and then we are doing the particular calculation. So this is how we are doing in this particular Nicholson method. Then we can see that amplification factor, the final factor gk is 1 minus alpha 1 minus cos k delta x 1 plus alpha 1 minus cos k delta x. So alpha and 1 minus cos delta x are positive. The denominator of the first expression is always greater than the numerator. So this is the absolute value of g that we will get from this particular example. So here we can see that how we are calculating the particular amplification factor, and then we can calculate this. Now we will take a small example here, that using this particular FTCS implicit form you have to solve u1 is equal to uxs, and the values are given to us here L, M, T, Ti, Fx, and the different values are given to us here. So what we will do is that we will make the calculation now. Here we made the calculation here, that initial heat distribution we calculate Fx, boundary condition for T1, then the amount of the time steps T, amount of the space point M, and then the space interval T. So here we can see that all the particular values, we can see in this particular figure also that here the different values are there, and we are writing this to solve this. So it becomes the different variables. So whenever we want to use the expansion, either it is a Taylor's expansion that we want to use or any expansion, by using this value we can easily calculate that particular values. So we can see here that the different values are given. Again I repeat, space interval is given, which is L is equal to 1, amount of space point is given to us, which is M is equal to 10, amount of space steps is given, which is T is equal to 30, then the boundary condition is given, which is T1 is equal to Tr is equal to 0, then the initial heat distribution Fx is given, which is 4x 1 minus x. So all these values are given, and we can see that there is a particular change in the particular variables, and from here using this particular expansion then we can do it. We can use the particular value, we can use the expansion in series that we want, either it is Taylor's expansion or any kind of expansion that we want to do, we can do it. Example number 2 is given, where we have to use the implicit BTCS method to solve ur is equal to uxs. Again the different values are given to us. Again we can see that we have to form the equation in terms of minus L and T, ux Lt is equal to 0. So again we have to calculate the different parameters. So first we calculate the space interval, L is equal to 5, then we calculate the space decreasing step, which is delta x, here we can see it is 0.1, then the time we can see T is equal to 200 here, amount of time in steps is 200, and then delta T is 0.05. So we can see that here all the particular values we will put in this particular equation, and then we generally solve this. So basically that how we take and read this particular value, and after that we can put in the equation, and then we can do a particular series or particular expansion, then do it. Then another example is given here, where again we are giving the space interval L to be 1, then the space step is delta x to be 0.1, then time step is given to us as 0.05, amount of the time steps is t is equal to 15, the boundary condition is given us as T1 is equal to 2, Tr is equal to 0.5, both the boundary steps are given to us. So the heat diffusion is also given Fx, which is 2 minus 1.5x plus sine pi x. So here the different values are given to us, and from this particular different values we are making the particular calculation. Here in all the 2-3 examples that I have given, different values are given here, and from the different values we are forming the equation, and from the equation we will have an expansion, we will have an expansion in series and all to make the calculations of this. So here we can see that how the expansion is generally evaluated. Then we have color plot distribution. The color plot distribution is given here. Every color plot is given and the range is also given. So we will make a numerical calculation of this. We can make a numerical calculation of this also. When we have calculated this value, we can make a color plot according to this. So after the particular calculation of the numerical value, we can calculate the particular color plotting of this, which will also show the variation. So here what we need to learn is that after calculating the particular density, change in the density, then we are making all this calculation. We have to use a particular expansion. We are using the Taylor's expansion here, and after that we are from the particular interval we are making the calculation. In the different example I have shown you that how this particular examples are generally used and how we are calculating the different values in this and then forming the equation and then applying the series. This basically used to lower down the approximation, or in some method we have used how to calculate the difference in the two particular intervals or two particular position. Secondly, in some equation we have learned that how to use a central value also, that when we have to calculate the central value, then how we are calculating this particular central value. So we can use these particular things in this. Yeah, so we can see that how we can calculate the central value, and from that particular central value we can make the calculation. So every time what the effort is that to lower down the approximation method and calculate the difference between the two time and the two position in terms of the heat diffusion. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.